All right. All right. So today is 28th. So I hope all of you are clear about what is called a smooth map, smooth function, right? So concept of local coordinates, right? So you have a manifold M where you don't know, I mean, kind of anything. So why do we consider this manifold in this sense? Locally Euclidean and all this stuff. The main point is if you look at this f of x plus h minus fx by h and limit h tends to 0, this part does not make sense in arbitrary spaces, right? So this, of course, with some lambda h, this one you've done for Rn. Even that, this also doesn't make sense. Yeah, that is the problem. So x is there, x plus h may not be inside the space because the space is not a vector space now. All right. So this definition doesn't make sense at all. So what we need to go a little bit roundabout way. First, you map, you fix a point, look at a small thing that looks like Rn, go into Rn, and do whatever we do in this limit here in Rn, here in Rn, and then come back. So it is smooth, provided this whole thing is smooth. So function f from, let's say, whatever, some Rm. So this is in if C infinity implies, or if and only if, this if and only if, this map f composes phi inverse. So this is by definition C infinity, right? So this is roughly the picture you should be having in your mind, that we do not have this, the limit does not make sense anymore because x, a point x is there does not mean x plus h is there. Look at a sphere, right? You will not get x plus h. It will be in the same vector, same subspace, same vector space. So some part of it might be there, but x plus h may not be there when x is in the same. Of course. So there is a problem. So that's why we need to go about a little bit roundabout way, define smooth, a notion, create a notion of smoothness on a space which is manifold by through what can you do through what you can say by going into Rn under a homeomorphism. All right, this is what you should be having in your mind. But so this is again recap of smoothness. This is recap. Smooth map. Now the point is we need to do a partial derivative here. Right? The limit doesn't make sense, so how to do it? Right? And so first of all, partial derivative against, I mean, by which? So you need to have some variables, right? So what are variables? Yeah. Okay, so a notation. So here, let us fix some notation, or maybe a change of notation. Since I'm following the book by Rowing W2, so let's go with the notation he is using. Otherwise, you might find it difficult. So yeah, you'll see a lot of differential geometry book is quite complicated to read mostly because of the notations. So change of two notations actually. So coordinates in Rn will be denoted by R1, R2, Rn. The upper script. All right. So this is so this is the change. This is the change. From lower script we go into upper script. So lower script will come into the picture again with some other context, and then we'll have trouble in combining the notations. So let's make it the very beginning. Okay, so now and last time also we said that local coordinates. So yeah, so local coordinates. So suppose U and phi is a chart in, in a manifold M of dimension n, then we can define the coordinates x1, x2, xn on U such that xj is by definition. So this is the change. We put last time we put actually subscript. Now we want to change it to superscript because the book will be reading will have this notation. So xj is, what was xj? Can anybody tell me? What was the definition of xj?
RJ composed inside.
Rj compose phi, right? Yeah. So this is the definition. So you have, I mean, of course, components of phi, and it is just the jth component of phi you look at as a coordinate. All right. So now we want to take the partial derivative with respect to xj, with j upper script. All right. Now we want to look at partial derivatives with respect to xj. So what would be it? Right. So suppose f is a function m to r. Let's take r, smooth function. We want to say to define del f by del xj on u, right? So the coordinates are local, so you cannot go this one. You cannot do outside u. All right. So this is. So what would be it? Any guess? Yeah, I'll not ask reason, just a guess. Yeah, any guesses here? Come on, guess it. You should have some intuition by now.
So we take the partial derivative of xj in Rn,
Mhm.
the jth component, jth partial derivative.
No, partial derivative of what? Xj. Xj is a map from U to R. So you cannot take partial derivative of xj in Rn.
Rj phi, right?
Yeah, Rj phi. So that is Rj compose phi. So this is a map from U to R, right? Well, we want to define, of course, on U. That's fine. So you what you want to do is the following. So del f by del xj at the point P. At the point P, you define this to be del by del rj, right? Then which function you want to define? At the point pp, which function you want to do? Derivative of?
F combustion psi inverse.
Right. F compose phi inverse. All right. So this is the definition. So the point is you do whatever you want to do in Rn and come back. That's what we are basically doing. F is a smooth function, but then for all practical purpose, saying it is a smooth function, we are looking at this function only. So you take this partial derivative and define it to be this one. This is the notion you need to get habituated with. There is nothing new except the notations here. Everything is happening Rn. So calculus of Rn is the most important part. But this one is a notation. So when we work in a manifold or you do geometry in a manifold, then you'll be using these notations. You will not be using this whole thing again and again. So that part, I mean, it should sync with your thinking that whenever you are talking about this one, you have this. But this is on you only, right? This is true for all P in U. This is for all P in U. Outside, what happened? Take another chart, another coordinate system, and use again this. But then what happens in the intersection? Yeah. What happened at the intersection between two charts? Right? It should be a natural question. Yeah, what could happen? Can you get any guess? So another point which might not be in U. That means there will be another coordinate chart. So there will be another system of coordinates. So then what?
Sir, here it's completely dependent on the decision of what chart we are picking, right?
That is correct. Definition. Look, in local coordinate, this is correct. But the important theorems or important things which are actually independent of coordinate, that you will see. Here, for the partial derivative, for the working purpose, you'll see that things are depending on the coordinates. Everything is depending on the coordinates. But for all practical purpose, or geometry actually, whenever you will do some geometry and you will be using these things, and then you will see the way you are using it's independent of coordinate. Okay, so since you are habituated in working in Rn, so you have single coordinate system, there is no problem, right? Everywhere is the same coordinate system. Here, the coordinate system changes depending on the point. Now, what happens in the intersection? Right? It should change nicely. Right? Yeah, that is our next thing. But before that, let us give something. Uh, Actually, yes. So here it is p, right? So let me write this. Del f by del xj. Some small computation. This p, this is at p, right? So this is, I can write at p is del f compose p inverse del rj phi of p, right? So so this is, and this part you can actually see this is f del xj. You can do this pp, right? So this is what it's happening. We'll be using this part. So this is what it is. So this, look at this. Look at this. What is this? So look at this part. Look at this part. What is this? This is nothing but del f by del xj composed with p inverse at pp, right? Now see, del f by del xj is also a function on u. Now this one is same as this, right? Which is a smooth map, right? So here we can conclude. So from here we can conclude that del f by del xj is also a smooth map on U. Fine. Any question here?
So can you repeat the argument?
So this one, you see here, I mean, P, for any point P, you can write this P to be P inverse Phi P, right? Which is nothing but this del f by del xj composed with Phi inverse, right? This one, composed with Phi inverse, right? Phi inverse of Phi P, which is P, nothing but, right? But this is the definition. This part is the definition. This part is the definition.
Sir, how are we concluding it's smooth?
Because when you, by definition of smoothness, you compose with the function with phi inverse, and if it is smooth, then it is then always then the function is smooth. So we get this, right, and this is equal to this part, and this is smooth, right? This partial derivative with respect to rj, sorry, rj, j will be upper script again. This is my mistake. Yeah. See, I'm also habituated with look script downstairs. Let me correct this.
Sir, like a counter example, like if I have x power 1 by 3, it is, we can't say it's smooth, but then we can say that x power 1 by 3 composed like x cube is.
Oh yeah, so it is a smooth
So-
map from r comma identity to r comma x cube. So if you give the chart map x goes to x cube, then x goes to x to the power 1/3 is a smooth map. So it depends on the coordinates you are giving. Chart map you are giving, right?
Yes, sir, we proved that if we compose two smooth functions, we get the smooth function. Here, it's not like that, right?
Oh no no no! I'm not using composition here. So, do you remember what we did? That R with identity, that atlas, is equal to is actually diffeomorphic to R with phi, where phi x equal to x cube. Do you remember
Yes,
that?
sir. Yes, sir.
So for that, what was the map we have taken?
X 1 by 3, x power 1
Right,
by 3.
right. So that became a smooth map, no? That became a smooth map. It was not composition with anything. Composition of two smooth map. This was smooth map, and it becomes smooth because on the right hand side you have taken the chart, not identity, rather x goes to x cube. So that part was very important. Yeah, is it clear, or do I need to explain again?
Yes, sir. It's clear.
All right. So here it is not composition of two smooth map. It is just definition of smooth map. For a map, let me, yeah, I don't have a space here. So let me do it again. So for a remark, this is not a remark. This is actually we have done it for a map A from U. Use a chart in M. We say F is smooth if F compose phi inverse. UP is a chart. So UP chart name if this is smooth. All right. So this one you check. This is not. This is by definition. So this is by definition. By definition, because U is also a manifold of dimension n. Right, and you are looking at, and it has single atlas U comma phi. That's good enough. Any question? So when you look at U map on U, you are considering U to be an independent manifold, and its atlas is U comma phi, single charted atlas. Now this is good enough, right? That's by definition. All right. So next, let's go to the question we are looking at. So question is, on the intersection, what happens? Oh, first of all, let us look at the following thing: the properties of partial derivative. Del xi by del xj is equal to delta ij. Right? It's supposed to be the case in Rn, and it's also here. So how do you see it? Proof? Used by definition, del xi by del xj. You treat that xi, xj as functions, as we know. So this is del by del rj, right? And this is ri compose, well, xi compose phi inverse, xi compose phi inverse, right? That was the definition. This was the definition. And now what happens? Xi compose phi inverse. So what was xi? Remember, recall. Recall xi.
RJ compose phi.
Ri compose phi, right? So this is del by del rj, ri compose phi inverse. So this is del rj by del ri, or del ri by del rj. Right? Which is delta ij. It's fine. So calculation becomes very simple. So a lot of time has taken to to develop what is manifold, how it should be. So that's why the things are more precise now. All right. Any question in this calculation? Looks very simple, but the point is to get habituated to it. You have to do by your hand. All right. Now change of coordinate. Sorry. Suppose sometimes you will see in the books that that u x1 x2 xn and v y1 y2 yn are two coordinate charts. So this kind of statement is written. You might see this, but that means p is written as x1 x2 xn, right? So question is, what happens to the partial derivative of a function, derivatives of a function on function, let's say function f from u to r on u intersection b, right? So this is the question. What happens? You get two partial derivative, one with respect to xj and one with respect to yj. How does it relate it? So more precisely, on u intersection v, we get two partial derivatives of f, one with respect to xj and the other with respect to yj, right? The question is is how these two partial derivatives are related, right? What do you think? Do you have any intuition? Something coming from our end? Any intuition? So suppose you have two coordinates in Rn. How does it change? How does partial derivative change? Come on, answer this question. This is simple calculus in Rn. You have two coordinate system in Rn. Of course, both of them are global. How does the partial derivative with respect to those coordinate system uh, are related? Yeah.
We use chain rule.
What? Chain rule.
Yes, sir. Because if xj and yj are two different coordinate systems, then del f del xj will be uh,
Will be,
uh,
yeah, will be what? Yeah, you are on the right track.
I mean, we can take the global derivative. Then there you can apply the chain rule and then take the partial derivative from the Jacobian matrix.
This is change of coordinate, right? This
Yeah.
this is related to change of coordinate. So I mean, one partial derivative is actually one time. This you'll see later that lies in the tangent vector, and so it will be just I mean image of the change of variable matrix. Well, matrix you can view it as a linear transformation from space. In this case, Rn to Rn, and the image of it. So I mean, you can using chain rule, you'll get simply the expression, but it has a meaning. It has a deep meaning. So partial derivatives, the partial derivative operator, those will be considered as tangent vectors. We'll come to that after we finish these things. Maybe in a couple of lectures we'll go into tangent spaces. All right. So now, yeah. So you want to see the Jacobian matrix. So how is Jacobian matrix in this case, right? So you have a function function f, right? So we have what? We have function f, f from u to r, and so yeah, let's say u is this, and you have something called v, this part. So on the intersection, you can have partial derivative del by del xj. So del f by del xj and del f by del xj, del yj. I mean, how this are related? That is the precise question. All right. Now, how do you get yj in terms of xj? right? That is one you one need to check. How do you get yj in terms of xj? Yeah, can you tell me? How do you get yj in terms of xj? What is yj? Okay, let me draw another picture. Maybe it's not getting clearer. This is u, this is v, and here, suppose the function is defined from here to r, right? This is the function f. Now on that, under phi, you have some space here, Rn, Rn. This one under psi, which is y1, y2, yn, you have some space here. In Rn also, right? Now, when you look at partial derivative with respect to xj, you need to consider this map. When you do partial derivative with respect to y, you need to consider this map, right? So when you consider this one, you need to come from, so go this and this to get this one, right? So let me write the definition again. Del by del xj of f is nothing but del f compose phi inverse by del rj, right? Yeah. Here Rn is the same coordinate. Now here you can write it del of f compose phi inverse f compose psi inverse compose psi compose phi inverse, right? This you can write by del rg. Yeah, is fine. Psi compose psi inverse, that is actually identity. Now what is this? Now you can use this is maps in Rn, right? So del by del Rj f compose psi inverse compose psi compose p inverse, right? And this you want to look at. So now use chain rule, right? So how do you use chain rule? Yeah, Praful, can you tell me what is chain rule?
Yeah,
Okay, tell
yes,
me
sir.
what.
D by
So
D by F compose psi
let me
inverse.
yeah, let me give you the setting. So suppose you have capital F and capital G, two maps, which is from, let's say, Rn to Rn, and then let's say it goes to R. This is capital G. Now G compose. So this is G compose F. Now del by del xj rj. So in Rn we are using our coordinate rj of G compose F. So what is it? We'll use first this one, then we'll use later that side. Yeah, tell me, Prabhu.
Yeah, yes, sir.
Yeah, what is it?
Yes, sir. Del by del Rj of G of f of that. I mean
Del by del Rj of G.
of
Let's say
f.
point P of Fp.
Yeah, f, any point that from
Then
into del f
del F
by del Rj.
del Rj. Is it correct? Otherwise,
Sorry. This will be del G by del f f f
del
p.
G by del F.
Sorry, what I'm telling.
You can coordinate, take coordinates as R1, R2, Rn in this side or and another side also. So this is also R1, R2, Rn, and this is, let's say, I mean, if you want to change, you can take S1, S2, Sn if you want to change. This might be now easier, right?
Yeah, sir, I'm confusing. Yeah, just give me a time.
Don't get confused in chain rule. And don't get confused in implicit and inverse function theorem. Yeah, Devanjit, can you tell me? Devanjit, are you there? Mugil Raj, can you tell me? What is it?
Yes, sir. 1 minute, sir.
But I think del G by del Sj should be. Then it's correct, I think.
SJ. Okay, so now you want to change this to Sj, right? Is it correct?
No, sir.
Yeah.
The summation.
Right, so that is the point. You have to use the summation, put it k here, k from 1 to n, and this. So never get confused with chain rule. So chain rule is one thing which will be always, you'll see the definition comes with the composition, right? No, so it will be used, I mean, anywhere and everywhere. So let us do it this chain rule. Let us apply here. So this is nothing but, here I use the same coordinates, or maybe different coordinates for this. Yeah, so R1, R2, Rn here, and S1, S2, Sn here. So this is nothing but we have two maps here and here. So it is summation k from 1 to n del f compose psi inverse by del sk, and then del by del Rj of psi compose phi inverse. All right. So this is C summation k from 1 to n. What is this? F compose psi inverse. F compose psi inverse in the definition, which is del F by del Yk. And this is del psi compose phi inverse by del Rj. Right? So you are actually using yeah, right. So and this is what? This is del by del x j of okay.
So even the second part can be simplified to del phi by del phi by del xj, right?
Del psi by del xj, right? Right. So del psi by del xj, that can be seen, yes. So yeah, this one, if you want to write it in even more in just x and y coordinate, yk del psi by del x j. All right. So this is the one. We'll write more precisely, or we'll see more interpretation along this way. But this is how it changes. This is how it changes. Now I mean, if you this is just one partial derivative. If you look at the whole partial derivative and look at how it changes, uh, I mean that you will see multiplied by some matrices. Some matrix multiplication is there happening, right? That you will see. Here also, see this part. This is. I mean, there is a little bit mistake. Can you see? What is the mistake? There is a little bit mistake here. So here, what is psi compose phi inverse? What is psi compose phi inverse? Right? This is a psi compose phi inverse map from Rn to Rn. So you cannot take this as just derivative like this. Right? It's a matrix. So it should be kth component of it. Should be kth component of it. Kth component. So kth component. Right? So what is kth component? That is nothing but what should you do? So this one, this is a map, and from where to where? This is a map from. Let's go back here. This is a map from this one. I went to this is it, right? Or the other way? Yeah, this is fine. Psi compose phi inverse. Now, what is jth component? So psi compose phi inverse compose jth component or kth component is Rk compose psi compose phi inverse. So here we need to write kth component. So this is nothing but Rk compose psi compose phi inverse. Right? Now this one, what will be this?
Rk compose phi.
Right. Rk compose psi, and which is nothing but I mean, instead of RK, I can do it SK, right? Yeah, that was my point. RK compose psi, right? Yeah,
So that'll be Yj then.
of course, YK,
Yk.
right? So this is del YK compose P inverse by del XK. Del RJ, and which is nothing but summation k equal to 1 to n del f by del yk phi inverse, remove phi inverse, what you get is xj. So this part is the Jacobian. I mean, member from Jacobian. Do you see this? Okay, so we'll deal with some more about partial derivatives, and on Tuesday in the last hour we'll have a short quiz about this smooth map and partial derivatives. All right. So yeah, okay. So I think that's it for today. Any question?
Sir, can you give a hint on how we can do the fact one you mentioned last class?
Which
About
one?
diffeomorphism, like if dimension is less than 3, then the atlases are same, like the maximal atlases are same up to differential diffeomorphism.
Oh, okay, okay. So this is a non-trivial theorem. This is not an easy one. So yeah, I can give you some material to read. Okay, so meet me. Those who are interested, just meet me in my office. Okay. So this is outside the course. So this is not contained of the course, and I'll give you some material on that. So in one dimension, it is rather easier, but in high dimension 2 and 3, it's a little more complicated. In fact, one can characterize what kind of manifolds could be there. Okay.
Yes, sir.
Okay. So yeah, I'll give some. Yeah. Any other question?